Find somewhere comfortable tonight. You don't need to follow any of this closely. You don't need to remember a single word. If you drift before we're finished, that's exactly right. That's the whole point of being here. Just let the words come to you the way warmth comes through a blanket, slowly, without any effort on your part. Tonight, we're going to talk about fire. Not the kind that flickers in a hearth, though there's something of that quality to it. A quieter fire. A fire that lives at the very center of matter itself, in a place so small it makes a grain of sand look like a continent. A fire that human beings learn to kindle, and then, with extraordinary patience and ingenuity, learned to hold. It is, in its way, one of the most remarkable things we have ever done. And it begins, as so many remarkable things do, with a single person walking down a street thinking, "We're in no hurry tonight. The day is already behind you. Let it stay there." It was a grey morning in London, September of 1933, and a Hungarian physicist named Leo Szilard was waiting to cross Southampton Row, somewhere near the corner of Russell Square. He was 35 years old, recently arrived from Berlin, recently fled from a Europe that was beginning to close around Jewish scientists like a fist. He had very little money and no permanent position. What he had, in extraordinary abundance, was the habit of thinking. The previous day, Szilard had attended a lecture given by the great New Zealand physicist Ernest Rutherford, who had declared with characteristic bluntness that anyone who spoke of deriving energy from atomic transmutation was talking moonshine. Rutherford was not a man given to understatement, and he was not wrong. Exactly. No one at that time knew of any practical way to release nuclear energy in useful quantities. But Szilard found himself troubled by the certainty of it. He had the kind of mind that could not leave a closed door alone. And so he was thinking, as the traffic moved past, about neutrons. The neutron had only been discovered the year before by James Chadwick in Cambridge. It was a remarkable particle, electrically neutral, about the same mass as a proton, found in the nucleus of every atom except the simplest hydrogen. Its neutrality was the key thing. Because it carried no electric charge, a neutron could drift into the heart of an atom without being repelled by the positive charge of the nucleus. It was, in a sense, invisible to the atom's electrical defenses. Szilard wondered, what if there existed an element, some element, perhaps not yet identified, whose nucleus, upon absorbing a single neutron, would release not one neutron but two? And what if those two neutrons each struck another nucleus, and each of those released two more? Then you would have 4, then 8, then 16. Each generation doubling the last, in a cascade that could, in principle, release enormous energy from a vanishingly small amount of material. The traffic light changed. Szilard crossed the street. And in the time it took him to reach the other pavement, the concept of the nuclear chain reaction had entered the world. He later described the moment with characteristic dryness, saying simply that it occurred to him that such a thing might be possible. But the implications he understood immediately and completely. This was not a modest idea. This was not a refinement of something already known. This was a glimpse into a new order of energy, one that dwarfed anything chemistry could offer, by a factor that was almost impossible to hold in the mind. To understand why, you need to understand something about what atoms actually are at their cores, and why those cores hold so much energy in the first place. An atom is mostly empty space. If you were to scale a hydrogen atom up to the size of a football stadium, the nucleus, a single proton, would sit at the center like a small marble. The electron would be somewhere in the outer seats, a speck of almost nothing, everything between them empty. This vast emptiness is what chemistry happens in, the interactions of electrons with other electrons, the making and breaking of molecular bonds. When coal burns, electrons are rearranging themselves. The energy released is the energy of electron interactions. But the nucleus is a different world entirely. Inside the nucleus of any atom heavier than hydrogen, you find protons and neutrons packed together in a space almost incomprehensibly small, roughly 10 to 15 meters across, which is to say about 100,000 times smaller than the atom itself. The protons in that space carry positive electric charge, and positive charges repel each other fiercely. The electromagnetic repulsion between two protons crammed into nuclear distances is enormous. By any electromagnetic reckoning, the nucleus should fly apart instantly. It doesn't, because of something else, something stronger. There is a force, physicists call it the strong nuclear force, that acts between protons and neutrons at very short range, binding them together with an attraction that, at those tiny distances, overwhelms the electromagnetic repulsion. It is the strongest fundamental force in nature by a considerable margin. But it has a crucial limitation. It only acts over distances comparable to the size of the nucleus itself. Step even slightly outside that range, and the strong force falls away to almost nothing, while the electromagnetic repulsion persists over much greater distances. This creates a situation of profound tension in heavy nuclei. Uranium, for instance, has 92 protons packed into its nucleus. Each of those protons is repelling every other proton electromagnetically, and the nucleus is large enough, just large enough, that the strong force binding the far ends of it together is stretched thin. The uranium nucleus is, in a real physical sense, barely held together. It sits at a kind of energetic tipping point, straining against itself. Now, here is where the energy comes from, and this is the part that is worth sitting with for a moment, because it is genuinely strange and beautiful. When protons and neutrons are assembled into a nucleus, the resulting nucleus has slightly less mass than the sum of its individual parts, not metaphorically, not approximately, literally less mass. If you were to place a proton and a neutron on a scale before they combined, and then weigh the resulting deuterium nucleus after they combined, you would find that some mass had simply vanished. It has not gone anywhere in the ordinary sense. It has become energy. The relationship between mass and energy, the idea that they are the same thing expressed in different forms, means that this tiny missing mass corresponds to a very real and very large quantity of energy, the energy that was released when the nucleus formed, the energy that now holds the nucleus together. This energy is called the binding energy of the nucleus, and it is what makes nuclear reactions so extraordinary compared to chemical ones. The binding energy per particle in a nucleus is roughly 1,000,000 times larger than the energy per particle in a chemical bond, 1,000,000 times. When Szilard imagined neutrons releasing more neutrons, what he was imagining, though the language of binding energy was still being developed, was a way to tap into this vast reservoir of nuclear binding energy by allowing heavy, strained nuclei to reorganize themselves into more stable arrangements, releasing the difference as heat and radiation. The particular element that turned out to be most useful for this was uranium-235. Uranium in nature is almost entirely uranium-238, with only about 7 atoms in 1,000 being uranium-235. The difference between them is 3 neutrons in the nucleus, and that seemingly small difference has enormous consequences. Uranium-235, when it absorbs a slow neutron, becomes so unstable that it tears itself apart in roughly 60 quadrillionths of a second. Uranium-238 is far more reluctant to do this. The chain reaction that Szilard imagined depends critically on uranium-235, which is why, as we will come to understand, nuclear fuel must be carefully prepared to concentrate it. But all of that engineering came later. In 1933, Szilard had only the idea, and he was frightened by it. He was frightened not because the physics was wrong, but because he sensed it might be right, and he had lived through enough of European history to know what human beings did with powerful things. He filed a patent on the concept of the chain reaction with the British Admiralty, and then he wrote to them asking that it be kept secret. He sat alone with the knowledge that he had imagined something immense, something that could warm cities or level them, and he wanted, for a little while longer, to keep it from the world. There is something very human in that. The discovery of a great power and the first instinct not to announce it, but to hold it quietly, to think carefully about what it means. The neutron, that small, neutral, unhurried particle, drifting through the world without charge, without announcement, it was the key to everything that followed. 9 years passed between Szilard's moment on Southampton Row and the afternoon when his idea became a physical reality beneath the concrete stands of a sports stadium in Chicago. 9 years of physics, of politics, of war arriving in Europe and spreading outward, of scientists scattering across borders, of letters written in urgency and coded in careful language. By December of 1942, the world had changed almost beyond recognition. And in a converted squash court under the west stands of Stagg Field at the University of Chicago, a group of scientists was assembling something that had never existed before. They called it Chicago Pile 1. The name was deliberately plain. A pile. A stack of material. Nothing to attract attention. What it actually was the world's first artificial nuclear reactor. The man at the center of it was Enrico Fermi, an Italian physicist who had fled Mussolini's Italy in 1938 after accepting his Nobel Prize in Stockholm and simply not returning home. Fermi was, by the accounts of everyone who worked with him, an unusual combination, a theorist of the highest order who was also deeply comfortable with the physical, practical work of experiment. He could calculate the behavior of neutrons in his head to a precision that astonished his colleagues, and he could also stack graphite blocks with his own hands, which he did day after day as Chicago Pile 1 took shape. Before we can understand what Fermi built, we need to understand what had been discovered 4 years earlier, because it was that discovery that made everything possible. In December of 1938, in Berlin, the chemists Otto Hahn and Fritz Strassmann performed an experiment that puzzled them deeply. They had been bombarding uranium with neutrons, expecting to produce elements slightly heavier than uranium, as previous experiments had suggested. Instead, when they analyzed the products of the reaction, they found barium, an element roughly half the mass of uranium. This made no sense under any existing model of nuclear reactions. Barium had no business being there. Hahn wrote urgently to his longtime collaborator Lise Meitner, who had recently fled Germany to Sweden after the Nazis' racial laws had stripped her of her position. Meitner was Jewish. She had escaped with 10 marks in her pocket and a diamond ring given to her by Hahn, which she had used as emergency currency at the border. Now, in exile, she received Hahn's letter describing the impossible barium. Meitner and her nephew Otto Frisch worked through the problem together during a walk in the Swedish snow around Christmas of 1938. What they realized, applying a model of the nucleus that had been developed by Niels Bohr, was that the uranium nucleus had not simply chipped off a fragment. It had split completely. The nucleus had behaved, under the stress of absorbing a neutron, like a liquid drop that had been set oscillating until it pinched in the middle and divided. Frisch, borrowing a term from biology, called this fission. Meitner's calculations, done in the Swedish snow with a scrap of paper, showed that each fission event released approximately 200 million electron volts of energy. An electron volt is the energy gained by a single electron moving across a 1-volt potential difference, a tiny unit by everyday standards. 200 million of them per event still sound small. But consider, Burning a single carbon atom in coal releases about 4 electron volts. Fission releases 50 million times more energy from a single nucleus than combustion releases from a single atom. The scale of the difference is almost geological. And then came the detail that changed everything. When the uranium nucleus split, it did not merely produce 2 mid-sized fragments, it also released, on average, 2 or 3 additional neutrons. Free neutrons, moving outward from the split nucleus at high speed, available to be absorbed by other uranium nuclei, each of which might then split and release 2 or 3 more neutrons, which might cause 2 or 3 more fissions, and so on. Szilard had imagined it in 1933. Now it was real. The chain reaction was not just a thought experiment. It was a physical consequence of how uranium nuclei behaved. The question that occupied the next 4 years was whether a self-sustaining chain reaction could be achieved in practice, whether the geometry and materials could be arranged so that enough of those released neutrons struck other uranium nuclei rather than escaping into the air or being absorbed by impurities. Most of the neutrons released by fission were moving far too fast to be readily absorbed by uranium-235. They needed to be slowed down, and slowing them down required a moderator, a material that could absorb the neutron's kinetic energy through repeated collisions without itself absorbing too many neutrons entirely. Fermi had worked on this problem extensively. His choice of moderator was graphite, pure carbon arranged in dense blocks. Carbon atoms are light enough to slow neutrons effectively through collisions, and graphite, if pure enough, absorbs relatively few neutrons. The purity was critical. Ordinary commercial graphite contained impurities, particularly boron, that would swallow neutrons greedily and kill the chain reaction. Fermi specified graphite of a purity that had essentially never been manufactured before, and the suppliers had to develop new processes to provide it. The construction of Chicago Pile 1 began in November of 1942. The team stacked graphite blocks by hand, layer by layer, building an ellipsoid that eventually rose to about 6 meters in height and used roughly 45,000 graphite blocks. Embedded within the graphite, at carefully calculated intervals, were lumps of uranium, both uranium oxide and pure metallic uranium, about 6 tons of metallic uranium and around 50 tons of uranium oxide in total. The uranium provided the fissile material. The graphite surrounding it would slow the neutrons to the speeds at which uranium oxide would absorb them most readily. Threading through the structure were the control rods. These were wooden rods coated with cadmium, a metal that absorbs neutrons with exceptional efficiency. When the cadmium rods were fully inserted into the pile, they captured so many neutrons that the chain reaction could not sustain itself. Pulling them out gradually would allow more and more neutrons to participate in fission, and the reaction rate would climb. On the morning of December 2nd, 1942, the team assembled in the cold squash court. There were perhaps 49 people present. Physicists, engineers, a few observers. George Weil, a young physicist, was stationed at the pile itself, ready to withdraw the final control rod by hand on Fermi's instruction. Another team member stood on top of the pile with a bucket of cadmium sulfate solution, ready to pour it over the graphite if something went wrong. A safety measure so basic it is almost touching, given what they were attempting. A set of neutron counting instruments registered the activity in the pile with a steady rhythmic clicking. Fermi directed the withdrawal of the control rods in careful stages throughout the morning. Each time a rod was pulled back and measured distance, the counting rate of the neutron detectors would rise, then stabilize, as the system found a new equilibrium below the critical point. Fermi would watch the numbers, perform calculations on his slide rule, nod, and instruct the next increment of withdrawal. He was building toward a specific moment with the patience of someone who knew exactly what the mathematics said was coming. Shortly after 2 o'clock in the afternoon, Fermi told Weil to withdraw the final control rod to a specific position. The clicking of the neutron counters began to accelerate, and this time it did not stabilize. The chain reaction had become self-sustaining. Each fission was producing, on average, at least one neutron that caused another fission. The pile was critical. For the first time in the history of the universe, at least the first time through deliberate human action, a self-sustaining artificial nuclear chain reaction was burning. Fermi let it run for 28 minutes. The power was tiny, less than half a watt, barely enough to light a small indicator bulb, but that was not the point. The point was that it was controlled, it was sustained. And it could be stopped, simply by reinserting the cadmium rods, which absorbed the neutrons and brought the reaction back below criticality in seconds. When Fermi ordered the rods returned, the clicking slowed. The reaction died away to background levels. The room was quiet. Someone opened a bottle of Chianti that had been waiting in a paper bag, and the team drank from paper cups. There were no speeches. Fermi was not a man for speeches, but one of the physicists present, Arthur Compton, made a brief phone call to James Conant, a chemist who was coordinating the broader project. The exchange was in loose code. The Italian navigator has just landed in a new world. Conant asked, "How were the natives?" Compton replied, "Very friendly." The fire had been lit, and it was, for the moment, entirely under control. It is worth slowing down here in this quiet hour to follow a single neutron on its journey, to trace it from the moment of its birth to the moment it causes a nucleus to divide, and to understand step by step what actually happens inside matter at those scales. Because the mechanism of fission is one of the most extraordinary things in physics, a process that happens in a space far smaller than any microscope can see, in a time far shorter than any clock can measure, and yet releases energy on a scale that changes the world. Let us begin with the neutron itself. A free neutron, drifting through the water or graphite of a reactor core, is a particle of almost exactly the same mass as a proton, carrying no electric charge, moving at speeds that depend on how it was produced. A neutron born from a fission event is a fast neutron. It carries roughly 2 million electron volts of kinetic energy and travels at perhaps 20,000 kilometers per second, which is about 7% of the speed of light. At that speed, it covers the diameter of a uranium nucleus in an almost incalculably short time. But as we will come to understand, that speed is actually a problem for sustaining the chain reaction. The neutron needs to slow down considerably before it becomes truly useful. For now, though, let us imagine a neutron that has already been slowed, a thermal neutron, as physicists call it, moving at roughly 2 kilometers per second, which is still fast by any ordinary standard, but is slow compared to a fresh-born fission neutron. This thermal neutron is drifting through the reactor core, and it encounters a uranium-235 nucleus. The nucleus of uranium-235 is a dense cluster of 92 protons and 143 neutrons, bound together by the strong nuclear force into a sphere about 12 femtometers across. A femtometer is 1/millionth of a billionth of a meter. If you were to scale that nucleus up to the size of a marble, the atoms surrounding it would be roughly the size of a large sports stadium. As our thermal neutron approaches, it feels no electromagnetic repulsion. It has no charge. It simply drifts in, drawn by the strong nuclear force as it comes within range, and is absorbed by the nucleus. This new nucleus has an extra neutron, and that extra neutron brings with it additional binding energy that is now trapped inside the nucleus, causing it to vibrate. Here is where the liquid drop model becomes useful, and it is worth pausing on this because it is a genuinely beautiful piece of physics. The nucleus of a heavy atom does not behave like a rigid solid sphere. It behaves more like a drop of liquid, held together by the surface tension of the strong nuclear force, capable of oscillating and deforming. When the uranium-235 nucleus absorbs a neutron and becomes uranium-236, the added energy sets the nucleus oscillating like a water droplet that has been struck. It elongates. It stretches into an oval. Then it stretches further, developing a waist in the middle, a narrowing as the two halves begin to separate. As the nucleus elongates, something critical changes. The strong nuclear force, which holds the nucleus together, is a short-range force. It only acts effectively between particles that are very close together. As the nucleus stretches, the particles at the two ends become farther from those at the other end, and the strong force between them weakens. But the electromagnetic repulsion between the protons does not weaken in the same way. It acts over longer distances. So as the nucleus elongates, there comes a moment when the electromagnetic repulsion between the two forming halves overcomes the strong force, trying to hold them together. At that moment, the nucleus splits. The whole process, from neutron absorption to the moment of splitting, takes on the order of 100,000 trillionths of a second, or about 10 to the power of -17 seconds. This is a duration so brief that light traveling at its full speed would cover only about 3 nanometers in that time. A single strand of DNA is wider than that. What emerges from the split are two fission fragments, two mid-sized nuclei, typically somewhere in the range of elements like barium and krypton, or strontium and xenon, though the exact split varies from one fission event to the next across a range of possibilities. These two fragments carry the bulk of the energy released by the fission event. They are launched apart by the electromagnetic repulsion between their positive charges, flying in opposite directions at speeds of roughly 10,000 kilometers per second, about 3% of the speed of light. That kinetic energy, the energy of the two fragments hurtling apart, accounts for about 80% of the total energy released by fission. And as those fragments tear through the surrounding material of the fuel rod, crashing into atom after atom, they shed that kinetic energy through countless collisions, each collision transferring a little energy to the surrounding atoms, setting them vibrating. The violent motion of the fission fragments becomes, within a tiny fraction of a second and over a distance of only a few micrometers, the warmth that heats the water that drives the turbine that generates the electricity. The remaining 20% of the fission energy is distributed among several other products. At the moment of fission, the nucleus also releases prompt gamma rays, high-energy photons of electromagnetic radiation, carrying about 7% of the total energy, emitted almost simultaneously with the split. These gamma rays are absorbed by the surrounding material and also contribute to the heat. And then there are the neutrons. Each fission of uranium-235 releases, on average, 2.5 neutrons. You cannot have half a neutron, of course, so in practice some events release 2 and some release 3, averaging to 2.5 across many events. These neutrons carry roughly 5% of the total energy as kinetic energy. They are the carriers of the chain reaction, the messengers that travel from one fission event to the next, ensuring that the fire continues. But here is the crucial complication. These newly born fission neutrons are fast, very fast. They carry about 2 million electron volts of kinetic energy each and travel at speeds that put them in the fast neutron category. And uranium-235, as it turns out, is not particularly eager to absorb fast neutrons. The probability of a uranium-235 nucleus absorbing a neutron, physicists measure this probability in units called barns, a unit with a name that comes from the wartime slang for something easy to hit, as big as a barn, is far higher for slow neutrons than for fast ones. At thermal speeds, the absorption cross-section of uranium-235 is roughly 500 barns. At the energies of fresh fission neutrons, it drops to fractions of a barn. The fast neutrons are, in a sense, moving too quickly for the uranium nucleus to catch them. There is also a further complication involving the far more abundant uranium-238. At certain intermediate energies, between the fast neutron regime and the thermal regime, uranium-238 has strong resonances in its neutron absorption, meaning it becomes very likely to absorb neutrons at specific energies. A neutron slowing down from fission energies passes through these resonance energies on its way to thermal speeds, and if it is absorbed by uranium-238 during this passage, it is lost to the chain reaction. Uranium-238 does not fission when it absorbs a neutron in this way. It simply becomes uranium-239, which eventually decays through a chain of radioactive steps into plutonium. So the newly born neutrons face a gauntlet. They are born fast, at energies where uranium-235 barely notices them. As they slow down, they pass through energies where uranium-238 is hungry for them. Only if they survive this passage and reach thermal energies do they become truly effective at causing further fissions in uranium-235. Getting them through that gauntlet safely, slowing them down quickly enough through enough collisions that they pass through the dangerous resonance region before uranium-238 can absorb them, is the central engineering challenge of the reactor core. And it is the problem that the moderator is designed to solve. The fission fragments, meanwhile, are not simply inert. They are neutron-rich. They carry more neutrons than is stable for nuclei of their size, and so they undergo radioactive decay, emitting electrons and gamma rays over timescales ranging from fractions of a second to many years. This ongoing decay of the fission products is what generates the residual heat that remains in a reactor core even after the chain reaction has been shut down. And it is why cooling a reactor core remains important even after the fission has stopped. The fragments are still warm, still releasing energy from their own internal rearrangements for a long time after the neutrons have gone quiet. This is the full picture of a fission event. A single slow neutron drifting in, a nucleus stretching and tearing apart in 100,000th of a trillionth of a second, two fragments flying apart at 3% of the speed of light, heat blooming outward through the fuel, gamma rays scattering into the surrounding material, and 2 or 3 new neutrons born and moving outward, each one carrying the possibility of beginning the whole sequence again. It is an extraordinarily compact event. Everything happens within a space far smaller than a living cell, in a time far shorter than any biological process. And yet the energy released by a single gram of uranium-235 undergoing complete fission is equivalent to burning roughly 3 tons of coal. The same energy. From a gram of material you could hold between 2 fingers. There is a beautiful simplicity at the heart of moderation, the process by which the reactor tames its own fast neutrons. It comes down to a principle that anyone who has played billiards can feel intuitively, even if they have never thought of it in physical terms. When a moving billiard ball strikes another billiard ball of the same mass head-on, it stops. All of its kinetic energy transfers to the struck ball, which rolls away at the original speed. But if that same billiard ball strikes a bowling ball, something enormously heavier, it bounces back, having barely transferred any energy at all. The bowling ball barely moves. The billiard ball carries almost all its energy away. Neutrons behave the same way. A neutron colliding with a heavy nucleus, like uranium-238, transfers very little of its energy. The nucleus is so much heavier that the neutron simply bounces off, slightly deflected but barely slowed. But a neutron colliding with a nucleus of similar mass, a proton for instance, which has almost exactly the same mass as a neutron, can transfer nearly all of its energy in a single collision. This is why ordinary water is such an effective moderator. The nucleus of ordinary hydrogen is a single proton, mass almost identical to a neutron. When a fast neutron collides with a hydrogen nucleus, it can lose the majority of its kinetic energy in that single encounter. After a relatively small number of collisions, on the order of 20 to 25, A neutron that began with 2 million electron volts of energy has been slowed to thermal speeds, carrying only a fraction of an electron volt. The whole slowing process happens over a distance of just a few centimeters in water. The catch, and there is always a catch, is that ordinary hydrogen also has a tendency to absorb neutrons, not just scatter them. When a hydrogen nucleus captures a neutron, it becomes deuterium, a heavier form of hydrogen, and that neutron is lost to the chain reaction. In a reactor using natural uranium, which is mostly uranium-238, with only 7 uranium-235 atoms in every 1,000, this neutron loss is significant enough to be a problem. Natural uranium reactors, like the Canadian CANDU design, use heavy water as their moderator instead. Water in which the hydrogen atoms have been replaced by deuterium, which scatters neutrons effectively but absorbs them far less readily. The most common reactor design in the world today, the pressurized water reactor, takes a different approach. It uses ordinary water as both moderator and coolant, but compensates for the hydrogen's neutron absorption by using enriched uranium as fuel. Uranium, in which the proportion of uranium-235 has been increased from the natural 7 atoms in 1,000 to somewhere between 35 and 50 atoms in 1,000, roughly 3 to 5%. With more uranium-235 available, the chain reaction can sustain itself even with the neutron losses to hydrogen absorption. The fuel itself, in a modern pressurized water reactor, takes a form that is worth picturing in some detail, because the engineering is quietly remarkable. The uranium is processed into uranium dioxide, a ceramic, a compound of uranium and oxygen that is chemically stable and has an extraordinarily high melting point, well above 2,800 degrees Celsius. This ceramic is pressed into small cylindrical pellets, each one roughly a centimeter tall and a centimeter in diameter, about the size of a pencil eraser. Each of those small pellets contains a quantity of uranium equivalent in energy, when fully fissioned, to roughly a ton of coal, or about 600 liters of oil. The energy density is almost beyond ordinary intuition. A material that looks like a small white chalk cylinder, holding within it the energy of a ton of coal. These pellets are stacked end to end inside long, slender tubes made of a zirconium alloy, a metal chosen because zirconium is exceptionally resistant to corrosion in hot water and, crucially, absorbs very few neutrons, so it does not significantly impede the chain reaction. These tubes, called fuel rods, are typically about 4 meters long and roughly a centimeter in diameter. Hundreds of fuel rods are assembled together into a fuel assembly, a precise rectangular bundle held in a structural framework. A large pressurized water reactor might contain around 200 of these assemblies arranged in the reactor core, representing a total of perhaps 90 tons of uranium. The geometry of this arrangement, the spacing between the rods, the distance the water travels between them, the precise density of uranium in the fuel is not arbitrary. Every dimension has been calculated to optimize the neutron economy, to ensure that the neutrons born in one fuel rod travel through enough water to be slowed to thermal speeds before they reach the next fuel rod, arriving as slow thermal neutrons that uranium-235 will readily absorb, rather than as fast neutrons that will mostly pass through or be absorbed by uranium. Let us follow a neutron through this geometry from its birth to its next fission. It is born in a fuel rod, fast, carrying 2 million electron volts, moving at roughly 20,000 kilometers per second. It exits the fuel rod, zirconium barely notices it, and enters the surrounding water. Within the first centimeter of water, it collides with a hydrogen nucleus and loses perhaps half its energy. It collides again and again, losing energy with each encounter, its path a random zigzag through the water molecules. After perhaps 20 or 25 such collisions, distributed over a few centimeters of travel, it has slowed to thermal speeds. It is now moving at roughly 2 kilometers per second, carrying only a 25th of an electron volt of energy. At this point, the neutron is drifting. It moves through the water in a gentle, diffusive way, bouncing off hydrogen and oxygen atoms, no longer losing significant energy but changing direction with each collision. Eventually, this wandering brings it back to a fuel rod. It enters the fuel rod, passes through the zirconium cladding, and drifts among the ceramic pellets of uranium dioxide. And if it encounters a uranium-235 nucleus, and at thermal energies, the probability of this is high. The cross-section is 500 barns, which is genuinely large on nuclear scales. It is absorbed. The liquid drop oscillates, and in 100,000th of a trillionth of a second, the nucleus splits, and the whole sequence begins again. The water in a pressurized water reactor serves a dual purpose throughout this process. It is simultaneously the moderator, slowing the neutrons, and the coolant, carrying the heat away from the fuel rods. The heat, generated by fission, by the fragments crashing into surrounding atoms, by the gamma rays being absorbed, by the ongoing decay of fission products, warms the water that flows between the fuel rods, and that warm water is then pumped out of the reactor vessel and through the heat exchangers that drive the turbines. There is an elegant self-consistency to this arrangement. The water that slows the neutrons is the same water that removes the heat. If the water temperature rises too much, or if the water begins to boil and form bubbles, its density drops. Lower density means fewer hydrogen nuclei per unit volume, which means less effective moderation, which means fewer thermal neutrons available for fission, which means the chain reaction slows. This is a natural automatic feedback. The reactor regulates its own power to some extent simply through the physics of water density without any deliberate intervention. This connection between moderator density and reactivity, the tendency of the reactor to produce less power when the water gets hotter, is one of the fundamental safety features of the design. It means the reactor resists the urge to run away with itself. It is built into the physics, not added on as an afterthought. But physics alone is not sufficient to keep a reactor in the precise steady state that operators want. For that, something more deliberate is needed. Something that can be adjusted by human hands or by machines responding to human instruction with a precision that matches the extraordinary sensitivity of the chain reaction. That is where the control rods come in, and where a tiny counterintuitive fraction of the neutrons turns out to be the most important thing of all. There is a number at the heart of every reactor, a single number that describes the state of the chain reaction at any given moment. Physicists call it the effective neutron multiplication factor, though it is usually written simply as K effective. It is, in essence, a measure of how many fissions the neutrons from one fission event go on to cause. When K effective is exactly 1, the reactor is in a state called criticality. Each fission event leads, on average, to exactly one more fission event. The chain reaction neither grows nor shrinks. Power output is steady. This is the state a reactor is designed to live in during normal operation, balanced on this precise point, like a ball resting in the bottom of a bowl, stable, unhurried. When K effective rises above 1, even very slightly, the chain reaction begins to grow. Each generation of fissions produces slightly more neutrons than the last, and the power climbs. When K effective falls below 1, the reaction fades. Each generation produces fewer neutrons than the last, and the power declines. The reactor operator's job, in its most fundamental form, is to keep K effective exactly at 1, or to move it deliberately above or below 1 in a controlled way when a change in power output is needed. The primary tool for doing this is the control rod. Control rods are long, slender rods made of materials with a very high affinity for absorbing neutrons. Boron and hafnium are the most common choices in modern reactors, though cadmium was used in early designs like Chicago Pile 1. When a neutron encounters a boron atom, there is a high probability that the boron will simply absorb it, swallowing the neutron, incorporating it into its nucleus, and removing it from the chain reaction entirely. The neutron does not cause a fission, it does not produce more neutrons, it simply disappears. By inserting control rods into the reactor core, operators increase the rate at which neutrons are absorbed by non-fissile material, reducing K effective below 1 and causing the reaction to fade. By withdrawing the rods, they allow more neutrons to survive and reach uranium-2035 nuclei, raising K effective toward and above 1, allowing the reaction to grow. In a full emergency shutdown, what reactor operators call a scram, all control rods are driven rapidly into the core simultaneously, absorbing neutrons so aggressively that K effective drops far below 1 and the chain reaction stops within seconds. The physics of control rods is straightforward. The engineering challenge is precision. The rods must be positioned to within millimeters, their movement controlled smoothly and reliably, their materials chosen to remain stable under years of neutron bombardment and high temperature. But the deeper challenge of reactor control is not mechanical at all. Consider what would happen if all the neutrons produced by fission were prompt, released at the instant of fission within a fraction of a microsecond. In that case, any change in K effective would propagate through the chain reaction at the speed of the neutron generation time, the average time between one fission and the next fission it causes. In a thermal reactor, this prompt neutron lifetime is on the order of a 10,000th of a second. If K effective were even slightly above 1, say 1.001, the chain reaction would double in power roughly every second. At 1.01, it would double every tenth of a second. At 1.1, it would double every few milliseconds. These timescales are far too short for any mechanical system to respond to. A control rod that needs to travel 30 centimeters to absorb the necessary neutrons simply cannot move fast enough to keep pace with a chain reaction that is doubling every millisecond. If reactors relied solely on prompt neutrons, they would be, in any practical sense, uncontrollable by human operators or by any mechanism we could build. But they do not rely solely on prompt neutrons, and this is where something genuinely remarkable enters the story. When a uranium-235 nucleus fissions, the vast majority of its neutrons, more than 99%, are indeed prompt. They are released within a fraction of a microsecond of the split. But a small fraction, less than 1% of all the neutrons produced, are not released immediately. They are released later by certain fission fragments, as those fragments undergo their own radioactive decay. These are called delayed neutrons. The fission fragments are neutron-rich nuclei. They have more neutrons than is stable for nuclei of their size, and they shed this excess through a series of radioactive decays, emitting electrons in a process called beta decay. Some of these neutron-rich fragments, after emitting an electron, find themselves in a highly excited state from which they promptly emit a neutron. This neutron is a delayed neutron, born not at the moment of fission, but seconds or even minutes later, after the fragment has had time to undergo its beta decay. The delayed neutrons come in several groups, each associated with a different type of fission fragment decaying on its own characteristic timescale. Some are emitted within fractions of a second, others take tens of seconds. The longest-lived precursors, the fragments that eventually emit delayed neutrons, have half-lives of up to about 55 seconds, meaning that some neutrons from a given fission event are not born until nearly a minute after the original split. Now, less than 1% might sound insignificant, but its effect on reactor control is transformative. Because of the delayed neutrons, the effective average time between one fission event and the next is not the prompt neutron lifetime of a 10,000th of a second, It is a weighted average that includes the long waiting times of the delayed neutrons. This effective generation time stretches to somewhere around 12 seconds in a typical thermal reactor. 12 seconds, not a 10,000th of a second. What this means in practice is that a reactor operating at criticality, even with K effective slightly above 1, responds to changes in control rod position on a timescale of seconds to minutes, not microseconds. The power climbs slowly enough that instruments can measure it, operators can observe it, and mechanical systems can respond to it. The delayed neutrons are a natural break, built into the physics of fission itself, that makes human-scale control of a chain reaction possible. Reactor designers exploit this property carefully. A reactor is always designed so that it is not quite critical on prompt neutrons alone. The prompt neutrons by themselves would give a K effective slightly below 1. It is only when the delayed neutrons are included in the count that the reactor reaches criticality. This condition is called delayed criticality, and it is the normal operating state of every power reactor in the world. The practical consequence is profound. To make a reactor run away on its own, to achieve what is called prompt criticality, where the chain reaction is self-sustaining on prompt neutrons alone, without waiting for the delayed fraction, you would need to raise K effective significantly above 1, far beyond the small perturbations that normal operation involves. The delayed neutron fraction acts as a buffer, a margin of safety that keeps the reactor in a regime where measured, unhurried adjustment is always possible. This is also why the enrichment level of reactor fuel matters so much from a safety perspective. Weapons-grade uranium is enriched to 90% or more uranium-235. At that concentration, the geometry of the material can be arranged so that prompt criticality is achieved very rapidly, and the chain reaction runs away before any delayed neutron dampening can help. Reactor fuel, enriched to only 3 to 5%, cannot do this regardless of how it is arranged. The geometry and enrichment together ensure that the reactor lives comfortably in the delayed critical regime, where the physics itself slows everything down to human pace. It is worth sitting with this for a moment. The thing that makes a nuclear reactor controllable. The thing that transforms an otherwise incomprehensibly fast chain reaction into something that operators can manage with instruments and rods and steady hands, is a small fraction of neutrons that simply take their time. Less than 1% of all the neutrons born in fission, arriving late, wandering in from the radioactive decay of fragments that were themselves born from a split that happened a minute ago. These slow, patient, delayed neutrons are the reason the reactor can be guided at all. They are the natural gift that makes the whole enterprise possible. The chain reaction hums in the core. Neutrons drift and are absorbed. Nuclei split. Fragments fly apart and shed their energy as heat. The fuel rods grow warm, hundreds of degrees warm, far warmer than any ordinary fire. And now the question becomes, what do you do with all of that heat? The answer, in a pressurized water reactor, begins with a decision that might seem counterintuitive. You keep the water liquid. Water boils at 100 degrees Celsius at sea level at ordinary atmospheric pressure, but the boiling point of water rises with pressure. At very high pressures, water remains liquid at temperatures far above what we think of as its boiling point. A pressurized water reactor exploits this by keeping the primary cooling loop, the water that circulates directly through the reactor core, under immense pressure, roughly 155 times atmospheric pressure. At that pressure, water remains liquid, even at 325 degrees Celsius. This superheated liquid water, far hotter than any ordinary boiling water, but still dense and liquid because of the pressure, flows continuously through the reactor core, absorbing heat from the fuel rods, and is then pumped out of the reactor vessel through large pipes to a component called the steam generator. The steam generator is where the energy crosses from the reactor's primary world to the outside world. Inside the steam generator, the hot primary water flows through thousands of slender tubes, each tube carrying intensely hot, high-pressure water. On the outside of those tubes, a separate supply of water, the secondary loop, kept at lower pressure, is in contact with the hot metal. The heat from the primary water conducts through the tube walls into the secondary water, which is at low enough pressure that it boils readily at these temperatures. It boils into steam. This arrangement, two separate loops of water that never mix, is deliberate. The primary water, having passed through the reactor core, carries traces of radioactive material, principally atoms that have been activated by neutron bombardment. Keeping it entirely separate from the secondary loop means that the steam driving the turbines is clean, non-radioactive, and can be handled without the shielding that the primary water requires. The steam produced in the secondary loop is at high temperature and high pressure, and it is directed toward the turbines. A turbine is, at its heart, a wheel. A very large, very precisely engineered wheel with rows of carefully angled blades arranged around its circumference. Steam at high pressure expands as it flows, and as it expands it pushes against those blades, causing the wheel to spin. The kinetic energy of the expanding steam becomes the rotational energy of the turbine shaft. In a large nuclear power plant, there are typically several turbine stages in series. A high-pressure turbine that extracts the first portion of the steam's energy, followed by one or more lower-pressure turbines that extract further energy as the steam continues to expand and cool. The turbine shaft, rotating at either 50 or 60 revolutions per second, depending on the country's electrical grid frequency, is connected directly to a generator. The generator is built around a fundamental principle of electromagnetism. A changing magnetic field induces a flow of electrons in a nearby conductor. The generator contains powerful electromagnets on the rotating shaft, the rotor surrounded by coils of copper wire fixed to the outer casing. As the shaft spins, the magnetic field sweeps past the copper coils, inducing in them an alternating current. That current flows out through cables into transformers that raise the voltage for long-distance transmission and eventually out into the grid. The electricity that arrives at your home, that powers the light in the room where you are resting tonight, if it comes from a nuclear plant, has traveled through this chain from a neutron absorbed by a uranium nucleus to the kinetic energy of fission fragments, to the heat of water in a pressurized loop, to the steam spinning a turbine, to the rotating magnetic field of a generator, to the electrons moving in copper wire, to the electrons moving in copper wire. Each step is a conversion of energy from one form to another, and at each step some energy is lost as waste heat. This is an unavoidable consequence of thermodynamics, the physics of heat engines, which tells us that no heat engine can convert all of its heat input into useful work. A pressurized water reactor converts roughly 33% of the heat generated by fission into electrical energy. The rest must be disposed of. This is where the cooling towers come in. Those great, curved concrete structures, wider at the base and narrowing toward the top, that have become the visual symbol of nuclear power in the public imagination. The spent steam, having given up most of its energy to the turbines, is still warm. It is directed to a condenser, where it gives up its remaining heat to a supply of cooling water, often drawn from a river or the sea, and condenses back into liquid water, which is then pumped back to the steam generator to be heated again. The cooling water that absorbed the steam's heat in the condenser is itself then cooled, either by returning it to the river or sea at a slightly elevated temperature, or by pumping it to the top of a cooling tower and allowing it to trickle down through a stream of rising air. As the water trickles down through the tower, some of it evaporates, and evaporation is a cooling process. It removes heat from the remaining water, cooling it enough to be reused. The visible plume rising from a cooling tower is not smoke. It is water vapor, the evaporated fraction of the cooling water, condensing in the cooler outside air into a cloud of tiny water droplets. Entirely harmless, entirely water. Now consider the scale of what a single large reactor accomplishes through this chain of conversions. A modern pressurized water reactor, running at full power, generates roughly 1,000 megawatts of electricity, 1 billion watts, continuously. Over the course of a year of continuous operation, that is about 8,700 hours of full power generation, producing enough electricity to power a city of roughly 1 million homes. To generate the same electricity from coal, you would need to burn approximately 3 million tons of the stuff. Trains of coal cars stretching for hundreds of kilometers, vast mines, enormous quantities of carbon dioxide released into the atmosphere. The uranium fuel that enables this, a few dozen tons, sitting in fuel assemblies inside a reactor vessel about 4 meters in diameter. The enriched uranium that powers a reactor for a full year could fit inside an ordinary living room. Not stacked to the ceiling, just sitting there in its fuel assemblies, occupying perhaps the space of a large sofa and the floor around it. And the reactor runs quietly for months at a time without interruption. Nuclear plants have capacity factors, the fraction of time they actually generate power at or near full output, of around 90%. They do not stop because the sun goes down or the wind drops. They do not require continuous deliveries of fuel. They hum along, steady and patient, converting the binding energy of uranium nuclei into the electrons that flow through copper wire, heating homes and powering hospitals and keeping the lights on through every night and every season, with a consistency that no other source of energy quite matches. The heat becomes light. The split nucleus becomes the lamp in the hallway. The chain reaction, tamed and measured and held at exactly the right rate, reaches through all of those transformations to touch the ordinary world with something quiet and steady and warm. There is a principle in nuclear engineering that is sometimes expressed this way. Safety should not depend on anything going right. It should depend, as much as possible, on nothing needing to go right in the first place. This is a different philosophy from most engineering, where safety is achieved by building systems that work correctly. Nuclear safety is achieved, at its deepest level, by building systems where the physics itself resists failure, where the natural behavior of the materials and the geometry of the design push the reactor toward a safe state, not away from it whenever anything goes wrong. The first and most fundamental of these physical properties is the one we touched on when discussing moderation, the temperature coefficient of reactivity. This is a measure of how K-effective, the neutron multiplication factor, the number that determines whether the chain reaction is growing or shrinking, changes as the temperature of the reactor rises. In a well-designed reactor, this coefficient is negative. That means as the temperature goes up, K-effective goes down. As the reactor gets hotter, the chain reaction weakens. There are several reasons for this self-correcting behavior. One involves the fuel itself. As uranium atoms get hotter, they vibrate more. A vibrating uranium atom presents a slightly different effective size to an incoming neutron. Its motion causes a broadening of the resonance. Absorption peaks in uranium-238, meaning that more neutrons are absorbed by uranium-238 at intermediate energies on their way to becoming thermal neutrons. This effect is called Doppler broadening, after the same Christian Doppler whose name is associated with the shift in frequency of sound from a moving source, because both phenomena involve the way motion affects the apparent frequency of a wave, or, in this case, the apparent energy of a neutron interaction. As the fuel heats up, Doppler broadening steals more neutrons from the chain reaction, reducing K-effective. A second contribution comes from the moderator. As water heats up, it becomes less dense. Less dense water contains fewer hydrogen nuclei per unit volume, which means it moderates neutrons less effectively, which means fewer thermal neutrons are available to cause fission. Again, as temperature rises, the chain reaction weakens. Together, these effects mean that a reactor has a built-in tendency to regulate itself. If something causes the power to rise, a control rod accidentally withdraws slightly, or some other perturbation occurs, the temperature rises and the physics responds by reducing K effective, damping the power increase. The reactor does not need a human operator or an automated system to notice the problem and respond. The physics notices it first and corrects it continuously and automatically on timescales of fractions of a second. This is the first layer of safety, the physics itself. The second layer is the fuel's physical form. The uranium dioxide ceramic pellets that make up the fuel are extraordinarily stable materials. Their melting point, as mentioned earlier, is above 2,800 degrees Celsius, far higher than any temperature the fuel would reach under normal operation, and far higher than the temperature it would reach even in most accident scenarios. The ceramic structure of the pellets also traps a large fraction of the fission products. The radioactive fragments produced by the splitting of uranium nuclei within the crystalline lattice of the material. The third layer is the fuel rod cladding, the zirconium alloy tube that surrounds each stack of fuel pellets. Zirconium is chosen not just for its low neutron absorption, but for its corrosion resistance and its mechanical strength at high temperatures. The cladding forms a tight, sealed barrier between the fuel and the cooling water. Even if a fuel pellet were to crack internally, the fission products would still be held within the metal tube. The cladding is the second barrier. The fourth layer is the reactor pressure vessel itself, a thick-walled steel container, typically about 20 centimeters of high-strength steel, that encloses the entire reactor core and the primary cooling water. It is also designed to remain intact under conditions well beyond normal operation. The pressure vessel is the third barrier. The fifth layer is the containment building, the large, reinforced concrete structure that surrounds the entire reactor system. Containment buildings are designed to the standard that they must remain intact, even if the reactor pressure vessel were to fail catastrophically, even if large quantities of steam and radioactive material were released inside. The walls are typically between 1 and 2 meters of reinforced concrete, designed to withstand not only internal pressure, but external impacts, including, in modern designs, the impact of a large commercial aircraft. Camisole. This layered approach, fuel ceramic, fuel cladding, pressure vessel, containment building, is called defense in depth. The idea is that no single failure, no single component failing to perform as designed can lead to a release of radioactive material to the environment. Multiple independent barriers must all fail simultaneously. And each barrier is designed to the standard that its failure is extremely unlikely, so the probability of all 4 failing at once is vanishingly small. Beyond these passive physical barriers, modern reactor designs incorporate what are called passive safety systems, systems that can keep the reactor cool and safe without requiring any active intervention, without pumps, without electrical power, without human action. In an older reactor design, cooling the core after shutdown required pumps to keep water circulating. And if those pumps lost power, as happened at Fukushima in 2011 when the tsunami disabled the backup generators, the cooling could fail. Modern passive designs work differently. They use gravity and natural convection, the tendency of hot fluid to rise and cool fluid to sink, to keep water flowing through the core without any pump at all. Water tanks are positioned above the reactor core. If cooling is needed, valves open and water flows downward by gravity without any power required. The hot water from the core rises, gives its heat to cooler water, and the cooler water sinks back. a continuous loop driven by nothing but the difference in temperature and density between hot and cold water. These passive systems are designed to operate for days or even weeks without any external intervention, giving time for operators to assess the situation and take deliberate, measured action without the urgency of an immediately failing cooling system. The temperature coefficient of reactivity also plays a role in accident scenarios. In the extreme case where a reactor loses all its cooling water, a loss of coolant accident, the loss of the moderator causes K effective to drop sharply below 1, and the chain reaction stops almost immediately. The residual heat from fission product decay still needs to be removed, which is what the passive cooling systems handle, but the chain reaction itself ceases without any control rod insertion, without any operator action, because the physics demands it. And then there is the fundamental fact of enrichment. Reactor fuel is enriched to 3 to 5% uranium-235. A nuclear weapon requires uranium enriched to 90% or more. The geometry and enrichment of reactor fuel are so far from weapon conditions that it is physically impossible for a reactor to produce a nuclear explosion. What can happen, and what has happened at Chernobyl in 1986, is a steam explosion or a chemical explosion from hydrogen gas produced when hot metal reacts with water, followed by a fire. These are serious events with serious consequences, but they are not nuclear explosions, and they are not in the same category of energy release. The Chernobyl reactor was also of a design, the Soviet RBMK, that had a positive void coefficient in certain conditions, meaning that as water boiled away, K effective initially rose rather than fell, the opposite of the negative temperature coefficient that modern Western designs require. This design characteristic contributed directly to the accident. Modern reactor designs in the countries that have adopted international safety standards do not share this property. The layers of stillness that surround a reactor core, the physics, the materials, the engineering, the architecture, are not simply a list of backup systems, they are a philosophy. The belief that safety should be woven into the nature of the thing, not bolted on as an afterthought. That the reactor, left to itself, should want to be safe. That the deepest level of protection is the one that requires nothing to go right, because it is built into the laws of physics themselves. It is a quiet kind of confidence, the confidence of something designed to remain still. The reactor runs through the night. It has been running all day, and it will run all tomorrow, and for the months that follow, steady and unhurried, its chain reaction held at exactly the right balance by the delayed neutrons and the control rods and the negative temperature coefficient and the quiet competence of the water flowing between the fuel rods. Outside, the world changes its weather. Seasons turn. But inside the containment building, behind the concrete and the steel and the ceramic and the zirconium, the same process continues, neutrons drifting, nuclei splitting, fragments shedding heat, water carrying that heat away through pipes and steam generators and turbines, and electricity flowing outward through cables into the dark. It is worth thinking from this still and quiet place about where this technology is going, not in an urgent or unsettled way, but with the same patience the reactor itself embodies. One of the most interesting directions is the development of what are called small modular reactors. The name describes them well. Compact reactor designs, generating perhaps 300 megawatts of electricity or less, small enough that the major components can be manufactured in a factory rather than constructed on site. A conventional large reactor, the kind that generates 1,000 megawatts, requires years of on-site construction, enormous cranes, bespoke components, and a workforce of thousands working for a decade. A small modular reactor, in some designs, can have its core components built in a factory under controlled conditions, shipped to the site and assembled. The construction time shrinks from a decade to a few years. The cost of the first unit is lower, and subsequent units built to the same design benefit from the experience of the first. Small modular reactors are intended not just for large electricity grids, but for applications that large plants could never serve. Remote communities in the Canadian North or the Alaskan interior that currently run on diesel generators, consuming fuel flown in by small aircraft at enormous expense. Industrial sites that need reliable, high-temperature heat for processes like hydrogen production or the refining of metals. Island nations and developing countries that lack the grid infrastructure to absorb a large plant's output. The modularity is the point, the ability to bring nuclear energy to places and applications where it has never reached before. In Canada, a project at the Darlington site in Ontario is working toward the installation of a reactor of the BWRX 300 design, a boiling water reactor scaled down and simplified compared to its predecessors, with passive safety systems that allow the core to cool itself for days without any power or pumping. The first concrete for that project represents something genuinely new, not just another large reactor, but the beginning of what its developers hope will be a factory-built, reproducible technology. Meanwhile, the fuel that existing reactors use is itself being improved. Accident-tolerant fuels are ceramics and coatings engineered to remain stable under conditions far more severe than normal operation, higher temperatures, longer exposure, more aggressive chemical environments. The goal is not to make normal operations safer, which is already very safe, but to extend the safety margin in any scenario that departs from normal, to buy time and options for operators dealing with unexpected conditions. Some of these fuels are already being loaded into operating reactors as part of systematic trials, replacing conventional uranium dioxide pellets with materials that hold their shape and contain their fission products more tenaciously under stress. There is also research into fuel with higher concentrations of uranium-235 than conventional reactor fuel, not approaching weapons grade, but enriched to perhaps 10 or 15%, a range called high-assay low-enriched uranium. At higher enrichment, fuel assemblies can be made smaller and more compact, which suits small modular reactor designs that need to fit within a tighter geometry. New enrichment facilities are being built to produce this material carefully and under international safeguards, as the designs that need it move closer to deployment. And then there is the fact that stays with you once you have heard it, like something half remembered from a very old dream. The Earth itself is a nuclear reactor. Not in the same way as the machines we have been describing, not a chain reaction, not fission in the controlled sense, but the interior of this planet is kept warm, in part, by the radioactive decay of uranium and thorium in the deep rock. These elements, present in the Earth's crust and mantle since the planet formed 4.5 billion years ago, are slowly and continuously releasing energy as their unstable nuclei shed particles and transform step by step into stable lead. This process has been running without interruption for the entire history of the planet. The heat it generates is not trivial. Roughly half of the Earth's internal heat, the heat that keeps the outer core liquid, that drives the convection currents in the mantle, that pushes the tectonic plates across the surface, that builds mountains and opens ocean basins and causes volcanoes to rise, comes from this slow nuclear decay. The other half is primordial heat, left over from the planet's violent formation, but that fraction would have dissipated long ago without the ongoing contribution of radioactive decay to replenish it. In a sense, the continents beneath your feet are drifting on a nuclear heat source. The mountains that have been raised and worn away over hundreds of millions of years were raised by forces ultimately powered by the decay of uranium. The volcanoes that have shaped so much of the planet's surface are venting heat that is, in part, nuclear in origin. The geothermal energy that some countries tap directly from the ground. Iceland heating its homes and greenhouses with water warmed by the Earth's interior is, at its deepest source, the energy of radioactive decay. We tend to think of nuclear energy as something new, something invented in the 20th century, something that arrived with Szilard's thought experiment and Fermi's graphite pile and the careful engineering of the decades that followed. And in one sense, it is. The controlled chain reaction is genuinely new, a human invention of the 1940s. But in another sense, nuclear energy is the oldest thing on Earth. It has been warming this planet from within since before there was life here, since before there were oceans, since the rock was still cooling from the heat of formation. The uranium in the deep mantle has been doing, in its slow and patient way, what Fermi's pile did in 28 minutes of controlled criticality in December of 1942, releasing the binding energy stored in heavy nuclei, transforming mass into warmth. There is something grounding in that. Something that places the whole story. Szilard crossing a street, Fermi stacking graphite blocks, the engineers designing containment buildings and passive cooling systems and small modular reactors, in a context that is older than human thought. The physics was always there. The energy was always there, locked in the nuclei of heavy atoms scattered through rock and soil. We found a way to release it deliberately, to guide it, to hold it in a careful balance and draw from it a steady, patient flow of warmth. The reactor runs through the night. The water circulates through the core, absorbing heat, carrying it away. The steam rises in the secondary loop and spins the turbine and turns the generator and sends electrons through copper wire into the world. The cooling tower breathes its quiet plume of water vapor into the dark air. The control rods hang at their calibrated positions, ready to absorb a neutron if one too many should drift where it is not needed. The delayed neutrons drift in, late, from the decay of fragments born a minute ago, keeping the response time slow and manageable and human. And somewhere, far from the reactor, the electricity that was heat, that was a fission, that was a neutron, that was a uranium-235 nucleus at a tipping point. The lamp glows softly. Someone is in bed. The day is already distant. The details of neutrons and moderators and pressure vessels and steam generators are dissolving now, softening at the edges, becoming less like information and more like the texture of a quiet evening. The chain reaction hums somewhere far away, steady and controlled, doing what it has been doing all day and will do all night, patient as the uranium in the deep rock, unhurried as the heat that has been rising through the earth for 4.5 billion years. The idea came to a man crossing a street. The fire was lit under a stadium in Chicago. The engineering grew, layer by careful layer, into something that holds enormous energy in perfect stillness. And so we leave it there. The reactor runs, the lamp glows. Somewhere behind you, the day is already very far away. Drift now, if you're ready. Clip well.